talk will be about, let me disable this. Oh. About research in catalysis done at MAX4. You mentioned that I worked the ambient pressure beamline called HIPPIE of MAX4, and fair part of my talk will be at the activities at this beamline, but I would like to give you impression on all possibilities for catalysis research at MAX4 and a little bit background about MAX4, why it's good in particular for catalysis research. So let's get started. Well, the topic is the catalysis research at MAX4, and we produce X-rays, of course, at the synchrotron. And the X-rays are in particularly good for looking into things sometimes literally, that is imaging, for example, sometimes not that forward through spectroscopy and structure. And there are all of these techniques and all these areas are good for understanding different properties and aspects of catalysis materials and processes. Why X-rays are so good? Well, first of all, they have variable penetration power, and that's related to their energy. So you can choose however you want to interact with your material, either penetrate it without destruction or let it interact with the material, but also without interaction. So it's non-destructive technique. The X-rays typically also have high flux and high spectral flux, meaning that we can do time result studies in multi-dimension, and I will explain a little bit more about these dimensions later. The X-rays are also non-contact probes, meaning that we can do more type of in situ and operando studies where we don't actively influence the environment of our samples, but just observe it. So that's essentially the graph. We have at the bottom, we have energy, that's our penetration power. On the left-hand side, this is some kind of intensity of our X-rays. What's important for catalysis in many cases, if not the most, not just the amount of photons per second for given energy, but amount of photons per second in given space and sort of confinement. And of course, the spectral bandwidths. This is called brilliance or brightness. This is what we need to maximize. And why is this important? Well, simply because so-called diffraction limit. So if you take a source of electromagnetic wave or light of photons, and if the source is smaller than the diffraction limit, which is proportional to lambda over the numerical aperture, then by using some kind of lens system, we can focus it down to that dimension, to the diffraction limit dimension, and that's the probe size that we can, for example, raster scan our sample and do maps of whatever properties we are looking for. If the source size is larger than the diffraction limit, then it starts influencing the size of the focus, and then compromise the resolution, the spatial resolution in particular. There are ways of bypassing it, for example, using secondary aperture, but that's cutting our flux and thus decreasing the brilliance. So what we want to do is decreasing the influence of the source size, and that's the source size and source divergence called emittance. So we need to lower it down to reach this diffraction limit, and that's exactly what MAX4 does or did differently from other synchrotrons. At least it was the pioneering of this fourth generation storage ring technology that bring the diffraction limit to high energies. And in this graph, you can see in orange color all the third generation. This is the current established technology or past established technology for the synchrotron storage rings, and they lie around this very nice line that connects the circumference of the ring and the emittance. And all the blue or green dots, they represent the fourth generation storage rings, out of which only the green ones are sort of operational rings. And MAX4, as I said, was the first one to be one of them and establish the technology. And you can see the big difference between these two groups, the third and fourth generation. So a lot of new science can and will be done using the technology that MAX4 brought. This is another graph showing superiority of MAX4 brilliance among similar facilities in the same range. So now coming to the science. So we discussed the accelerator part. Now let's discuss what we can do with these nice X-rays. The graph here shows 14 out of 16 currently funded beamlines, and these 14 beamlines are in various stages of taking users. Some been doing it for several years, some only go into user commissioning phase. But in principle, an outline in the green here, those beamlines that already actively involved in catalysis research, and the orange ones that will be involved in the research once they get into general user phase. But in principle, all of them can be involved in the catalysis research one way or another. And I could go and discuss every single beamline, but since we don't have enough time for that, we probably should focus on several examples. Talking about the catalysis research, I'm coming back now to this dimensionality of research in catalysis. You've heard many times about like 3D imaging, 4D imaging, 5D imaging. I like to think about it about 4 dimensions in the catalysis research. The 2 dimensions probably is most known for people who are in the catalysis community, especially who do surface science type of catalysis, model catalysis. And this is so-called pressure gap and material gap. So this is dimension of material complexity and a dimension of environment, the more complicated environment and more complicated material. And we would like to explore both of them. There is also another 2 kind of dimension. This is the time scale and the length scale. And all of these 4 dimensions we would like to explore in the catalysis. And I hope some of the examples shown below show you which dimensions we explore, and in particular, how we combine the exploration of these dimensions. Well, let's start looking at the examples. Here I started from the NanoMAX beamline. This is one of the flagship beamlines of MAX4 that is really, really hardly using the technology and the advantages of the storage ring. This is the hard X-ray nanoprobe beamline that is using nano-focused beam without any secondary apertures. To study a diffraction, to do nano diffraction and nano fluorescence spectroscopy to understand, for example, the distribution of electronic density or crystallographic phases and elements with these spatial resolutions. The beamline has quite a number of sample environments, and some of them are described here. For example, there is a sample heater, electrochemical cell, a nano-indenter, diamond anvil cell. Anything in principle that is small and light can be put into the holder in the positioning stage, can be used at NanoMAX. The scientific example shown here, this is quite interesting because this is a study in phase transformation in a nanowire. And this particular nanowire is the perovskite nanowire, which is useful for solar cells, for example. However, the nanomaterials, in particular nanowires, are also quite interesting morphological systems for catalysis. It's very relevant for catalysis as well. So what's been done here is X-ray diffraction, non-X-ray diffraction, and by scanning the beam through the wire. So here you can see, I hope you can see my laser pointer here. This is the nanowire, and every pixel here represents X-ray diffraction image, and the sum of all of them shown on the left-hand side. This is the sum of all the diffraction images through the whole wire. And this is done in situ. So they heat sample and see if there are any phase transformation at different temperatures. And you can see up to 70 degrees, not much going on in the nanowire. It stays pretty much amorphous. Whereas at 80 degrees, certain crystallization occurs in the nanowire. You can see here 3 distinctive diffraction peaks appearing that correspond to a creation of a new phase. And then you can study how this phase is stable, if you start cooling down or heating up, and indeed some of the phases disappear when you either cool down or heat up and then come back when you do it again. Another experiment that was done at NanoMAX was proof of principle, but I think it's quite important. That shows that that this particular type of measurement could be done after overcoming some of the small difficulties. This is the coherent imaging in Bragg conditions of gold nanoparticles, and this is done in electrochemical cell under operando conditions. So you have an electrochemical cell, and you apply voltages, you do some electrochemical reaction, and you measure, in this particular case, the stress distribution within a series of nanoparticles. And they prove that in principle it could be done, and this is due to the high coherent flux from NanoMAX beamline. The problem is this experiments that under the synchronous beams, the nanoparticles are so small they tend to rotate. So you need to have extremely fast data acquisition down to seconds or even sub-seconds in order to do all complete stress map. And in principle, that will be possible with the fourth generation storage rings. Moving from microscopy to spectroscopy beamlines, Boulder is one of the flagship beamlines that is specifically built for catalysis studies. They use X-ray emission and absorption studies to understand, again, atomic and chemical environment, atomical and chemical composition of samples and the different environment. And again, there are several sample environment exist at the beamline that provide different capabilities, especially for catalysis. And this is one of the examples of such a study. This is a comparison of real catalyst on the left, reduction of real catalyst versus reduction of synthesized nano catalyst. And the difference is in one case, it reduces, that could be clearly seen from the absorption measurement, whereas the new catalyst that is synthesized by specific method doesn't reduce. And this is done in the catalysis flow cell at 1 bar condition, as it's done typically in the plant. Coming to the soft X-rays, the LINXS is a photoemission beamline that has 2 branches. The surface and material science branch, this is using, in particular, interesting because it's using, it's a typical surface science type of instrument, but it's very successful and quite oversubscribed. It shows how much modern synchrotrons have a need to have very well-established techniques, because in the end, after having new materials, you want to just simply measure their properties in vacuum under very controllable conditions. Sometimes you just want to study very very basic ideas and very basic equations, and Beamlines instruments as FlexPS is very useful for that. One of the examples is a study thermal stability and search for active phases for iridium oxide layers. What was found in this study that unlike electrochemical stability, the thermal stability of iridium oxide is quite poor. It already decomposes at temperatures above 450 K, and formed iridium reduced clusters are active in binding, for example, CO or water, whereas the iridium oxide itself, the freshly prepared, is totally inert. Coming back to HIPPIE and species beamlines, where we run APXPS program, and the rest of the talk I will be talking about them. There are two beamlines. They cover slightly different ranges of X-rays because they're placed into different rings. But the main techniques there is ambient pressure photoemission. And this is the extension of standard vacuum photoemission that was used at FlexPS, for example, and it's aimed to do the same type of experiments, understanding chemical processes and interfaces between liquids, solids, and gases under environmental realistic conditions. These beamlines also provide different sample environments. And there are several different types of, or several different ways of creating these environments. And okay, I will not explain what the big difference are, but both species in HIPPIE have different type of cells that allow different types of sample environments that are tailored for a specific type of experiments or specific type of environments. For example, species has bread and butter catalysis cell that is focused on catalysis type studies, or ALD cell that is built for studies of ALD process itself. More cells are currently under development, like for photocatalysis, sulfur chemistry, and so on, electrocatalysis. HIPPIE also has a catalysis cell that attracts most of our users. Actually, we will have 2 cells by the end of this year. We have infrared spectrometer that is attached to the same setup, so we can measure absorption, vibration spectroscopy together with photoemission. Have electrochemistry cell that is very useful for electrocatalysis measurements, but it's also used as a development setup because it's big and so easy to access. And the examples I will show you later using most of these cells. Here, I would like to show you, so far I've showed you how to explore the complexity dimension that is studying real catalyst, the space dimension that is going to nanometer resolution. We also studied obviously the environment dimension. That this is the this is available at all of the beamlines that I mentioned, with the exception of FlexPS. Here I would like to focus on the now time dimension, how we can study dynamics of catalytic reactions and processes and different interfaces. The first example is the study of so-called undercover catalysis, how different catalytic reactions occur if they're confined in space by 2D material or graphene, for example. The intercalation of gases, different gases under graphene, is a very well established science, and it's known pretty well what happens with different gases if you start interacting them with different gases under UV conditions. If there is nothing happening, if there is a chemical reaction going on, or if it's or something is titrated, and so on. But the question is, what happens in the millibar regime if we bring conditions to more realistic conditions? Here I would like to show you only one example. This is the interaction of oxygen and hydrogen, oxidation of hydrogen on transition metal, anti-graphene. And what we did, and what was done here, and you will hear this a lot in the remaining talk. It was done, the partial pressure, or the gas composition over the catalyst was changed rapidly by pulsing of gases. And in this particular case, the pulsing was done by switching the mass flow controllers that can be done on the order of seconds to tenths of seconds. And this is seen in this graph. So on the left-hand side, you can see the oxygen and carbon as a series of oxygen and carbon spectra depicting in carbon in particular the shifts in graphene C1s level that are very sensitive to the underlying interface, let's say. If it's a pure iridium or some gas intercalated, and depending on the gas, the shifts are different. So in this case, graphene is a kind of a probe of what's going on under it. We have two types of gas pulses, the oxygen-rich and hydrogen-rich. And once you pulse the gas, one after the other one, you can see a change in the chemical composition on the covered graphene or undercovered graphene on the bare sample. And then you can do the time series. You can fit, you can plot it versus time, you can define the time constants as shown on the right-hand side graph. So you can correlate the gas phase composition or the composition of the reagents with the what's going on in the chemistry, that is the catalyst itself. In this particular case, the time resolution is on several tens of several seconds. If you want to study more fast processes, we need to slightly modify the method and choose the faster process. And that was done in the next experiments, where a CO oxidation reaction on a transition metal palladium was studied. This oxidation is pretty fast reaction, so a more fast method was fast acquisition was chosen. So if previously we were using if acquisition of about 1 Hertz per spectrum was used, 1 spectrum per second. In this case, on average 6.5 spectra per second was recorded. So the time resolution of this experiment was about 130 milliseconds. But again, it's the same type of experiment. You pulse gases. You have one composition, the CO-rich gas composition here, and then you switch to the oxygen-rich, and you try to see what's happening in this. Well, you see the surface composition and correlate with the gas composition in the pulse, in the other pulse, and in between. This figure, this picture shows a series of spectra, and this is oxygen 1s, just from one pulse with the 6.5 Hertz acquisition rate. You do actually see some of the changes here. The gas lines are kind of maybe not very well, but you can resolve them by your eye. There are some changes happening you can also barely see them. Some changes happening on the surface. However, if you look at the data spectrum per spectrum as shown here, it's just all the signal within the noise. So that's not really fitted, and you need to improve statistics. Fortunately, if you repeat this experiment over and over many times, and by many, I mean tens or even hundreds of times, with thousands of spectra, and then you use a very clever technique of aligning them, you can average and substantially increase statistics. And then again, from the same spectra, you suddenly get all of your information that you need. And then you can fit it with peaks that you want according to the chemical composition of your surface, and get correlation between the gas phase that is at the bottom and the surface phase. And the surface composition that's shown at the top. And then you can have the whole story, what's happening within the pulse, within CO-rich pulse, oxygen-rich pulse, CO-rich pulse, but also you can see what is going on in between, how the surface is switching between two different phases. In this particular case, with oxygen-rich phase, you have a native oxide that very inert with interaction with CO, but once you consume it and create metallic palladium, it very quickly becomes covered by CO and gets poisoned, so the reaction stops. So this is very good to know. However, one can go further down and see how exactly this conversion happens at the point where the metallic palladium starts, is still metallic. So you really need to focus in this range here and decrease the time resolution or increase the time resolution better than 130 milliseconds. So for that, we need to kind of slightly different setup. We need to have a pump probe technique that I'm sure all of us know from typical pump probe techniques used at the fields, when you have a laser as a pump and then a very short probe by X-rays, study ultra-fast phenomena. We can do the same in principle with XPS, but instead of using laser pulse, we can use pulses of gas. So as shown in this picture, this is standard setup. We have electron analyzer, X-ray our sample, and we have fast valve that is capable of opening and closing in a very short time. We can synchronize it through a delay generator with our detector, and do our pulses. And this is just an image showing how we do the pulses. This is just film rate video on the camera. This is not time resolved, not synchronized. It's just showing that we do really pulses. The frequency is 10 Hertz, so 10 pulses per second. But the duration of the pulse is very different. It's not 100 milliseconds, and I will show you in a bit how long it is exactly. How exactly do we do this measurement? Well, this is our pulse in time. We can measure it spanning from hundreds of microseconds to several milliseconds. Since we are synchronized with the detector to the pulse generation, we can measure only a short period of time, a particular XP spectrum only in this range, and then varying the delay between the generation of a pulse and our probe, we can probe the chemical composition of both gas phase and surface at different delays as it evolves. So that picture, the video I was showing you, it was a pulsing of nitrogen just in vacuum. We can fit the received data here as a function of a delay and show the intensity. You can see that it's here. The time is in microseconds here. We can also measure the surface composition. In this case, that was a platinum sample. I mean, you don't expect anything happening to platinum if you just dose nitrogen. But what you can see is the decrease in the intensity of platinum. It means that we run into the millibar regime. Here, so you can estimate, and the estimation gives us on the order of 0.1, 0.3, half millibar for different conditions. So we are really creating a millibar type of gas puffs that in very short time exposed to our sample and then do some of the reactions. In that particular case, the duration of this gas pulse was 180 microseconds, but also another way of claiming the time resolution is the rising age of 110 microsecond in this particular case. And I think this is a more important time because that gives the difference in the chemical composition, in the chemical potential from, and this difference can be huge. It can be several orders of magnitude. And we can, the idea here to correlate the composition of the gas phase to the surface. So with a small modification, then now we can leak another gas, a second type of gas directly to the sample constantly, and then pulse first gas to study their interaction on the surface. The reaction of choice is CO oxidation, obviously, on platinum, that particular case, because it's fast and it's quite easy to control. The video you can see here demonstrates this video array type of experiment. Let me run it again. Yes, now it's running. The two peaks on the left, this is oxygen doublet, the gas phase oxygen doublet. The peak which is appearing here, this is CO. So you can really see the background of oxygen and the pulse CO inside it. We can measure the individual spectra of the gas phase in different time delays. Some of them are shown here. And the first interesting thing we could see from this experiment is that, yes, we do have oxygen before the pulse and then a lot of CO within the pulse, but we don't see, for example, oxygen within the pulse. It means that the gas that we are pulsing in this particular case, CO, completely blows away oxygen. That really helps us establishing the difference in the chemical potential or partial pressure to several orders of magnitude and have this quick change from one gas to another gas. So this is the example from the fit. You can see the CO pulse now very long, about 5 to 6 milliseconds. But if you focus on this area where this transition happens, it's about 100 microseconds. So the transition between oxygen-rich conditions to CO-rich conditions happens only about 100 microseconds. The blue data here is the production of CO2. So sorry, if you look here, we do have a production of CO2, and it's non-negligible within the pulse. Now we can start playing with different parameters and exploring the parameter space. Some of them are done on purpose, some of them are just there in the end. But in principle, in all of the cases, you can see a switch between oxygen-rich and CO-rich conditions and production of CO2 that is picked about where this transition happens. We can do some analysis, and you don't have to remember or pay attention to most of these numbers. Maybe the important number is the CO2 signal width. That's the time where the CO2 is mostly produced. And again, this is a very, the variation in this number is very big, depending on the temperature and exact pressure. It can range from like 50 microsecond to 230 microsecond, but on the average, in our case, it was slightly more than 100 microsecond. The ratio between CO2 and CO, where maximum produced CO is about 14%. This is quite an important number for later. Now, the most interesting part, we try to correlate between the surface and the gas composition as this process happens. So we record oxygen 1s and platinum 4F from our sample. You can see in oxygen the gas phase components. Unfortunately, no CO2 production because the just noise levels so high, but very clearly see a switch between oxygen and CO rich phases. For the CO rich phase, you can definitely see CO on the surface. So these peaks correspond to bridge in the top CO, and also you can see platinum CO on top of platinum peak here. The oxygen rich phase, it's a little bit puzzling for me. So it seems like we have oxygen absorbed on the platinum, and it overlaps very nicely with the literature data. But then looking at the platinum, it seems like instead of having oxygen or even oxide sitting in platinum that would appear at high binding energy, we have reduction in platinum. So it seems like we clean our platinum, or there is another good interpretation. So if you have good ideas, I would be very glad to discuss them with you. But anyway, we can now correlate the components and the composition of the platinum surface by fitting these features with the gas phase component. The gas phase spectra for this particular experiment, we measure only one spectrum at 800 microsecond, but it happened to be right at the top where the CO2 mostly produced. You can see it by the ratio between CO and CO2 that happened to be 13%. So these are the correlation between surface and gas that I was talking about later. This is the switch between oxygen and CO phase in the gas, and this is switch between, well, I call it platinum, I call it oxygen and CO components on the surface, and you can deduce them from either platinum 4F or oxygen 1 spectrum. They're pretty much the same. And then using either gas phase data or that table that you saw before, you can position the production of CO2 peak somewhere here. And in reality, the difference is so small that it's practically negligible. So CO2 is being produced where CO and oxygen in gas phase is approximately the same, and it pretty quickly stopped while you have CO rich conditions. Now we can put here our surface data. That's the shown by squares and circles here. And again, the difference between two graphs is we are using the gas phase data or the statistical data. That's the correlation we would like really to see. And what does it tell us? Well, for example, the CO is being produced where the maximum CO coverage, very close to the maximum coverage in platinum. It also tells us that CO2 starts being produced where very little CO is present on the surface. Yeah, so with this we can say that we can reach time resolution of about 100 microseconds on the rising edge within this 0.1, 0.3 or half millibar gas pulse, and we can correlate the gas composition with the surface composition on the sample. So with this, this is the second to last slide. I just would like to mention some of the other beamlines that were highlighted in orange in one of the first slides. Those beamlines will provide also quite great capabilities for doing catalysis at Max 4 using different techniques. So with this, I would like to finish, and I would like to welcome to Max 4 to do research in catalysis. Thank you.
Well, thank you very much, Andrey. Very nice overview of Max 4 and catalysis-related research. So now I'm asking the audience whether they have some questions to Andrey. So now I have to be on the lookout here somehow. You can raise your hand or you can just shout. See it. Yeah, I don't see anything. So I guess while you're thinking about question, all of you other guys, I can ask some questions. So, I mean, you are using the pulsed experiments to increase the time resolution, right? As far as I understand. As far as I know, people maybe in more applied experiments, they also pulse the gases in order to increase the the product yield. Is that anything you can say anything about from your measurements?
This is one of the things that I don't have time. I didn't have time to really check and compare, but this is on my to-do list. Yeah, for the data analysis.
Yes.
But yeah, you are right that the pulsing could be great to increase the reaction rate, because you, as for example was shown in the young experiments, you switch between two inactive phases here, and if you repeat this switch, then obviously the transient production is high than the steady state.
Yes, this is interesting. Yeah, so did anyone come up with any questions so far? No, it doesn't look like. So I can ask another question. Now I can ask questions. So as far as I know, at Balder, you can do absorption spectroscopy and diffraction at the same time. That must be useful for quite a few people, I suppose. So, and then the follow-up question is then, when it comes to gas phase catalysis, so how is the situation with the gas in terms of safety at Balder at the moment? Do you know that?
Yeah, well, related to the first question, yes, you can study, there are different techniques that are implemented at Balder, and some of them you can really combine. I just described those that are currently available for the users. You literally go to the Max 4 website and see that the XES and XAS are accessible, but combination of techniques, this is one of the things that some of the beamlines, many of the beamlines I'm thinking about, that you can get structural and spectroscopical information at the same time from the same spot. Related to the gas safety, Balder is one of the most critical and most difficult beamlines, because in that particular case, it was, if I'm not mistaken, 2% of hydrogen in atmospheric pressure of nitrogen, but they can go to pressures that are really used in industry. So the safety implications are much stronger than for emission beamlines, where we typically work with gases. So the level of complexity for the gas line is higher and bolder, thus the project is requiring more attention. It is moving forward, but it's moving forward at I wouldn't say the slow pace, but at a pace that it takes.
Yes.
To build a completely new gas system, gas line and it's really the first two gas lines at HIPPIE and the Boulder that is being built right now.
Okay, so so far no other questions. So I still have some time, so I can ask a final question. So when it comes to the electrochemical XPS, for instance, at HIPPIE, then so quite a few people wants to go, into a regime where you start to create bubbles, in some way or another. Can you comment on that somehow?
Yes, I didn't touch it, the electrocatalysis at all, HIPPIE, because we don't have very nice complete stories from electrochemistry cell. There are for batteries, but I thought, well, batteries maybe not so useful. Although there are many groups. I mean, you'll be doing some of this yourself. The method which we have currently available at HIPPIE is the dip and pull method that does rely on the creation of very thin films, and by having them thin, you can access solid liquid interface. So the problem is with thin films, they cannot really resist high currents, ion or electrical currents. And if you start creating bubbles, you probably will use up all the material from this very thin film very quickly. So that is not so good for this type of experiment. However, there are other developments in the world that we would like to have and have plans to have that are capable of such types. There are membrane-based cells that can go to current limited, not potential limited electrochemistry experiments.
Okay, so there seems to be some future there also.
We do have collaboration with Fritz Haber, who have developed it. We just need essentially people who would do that.